In this section, we'll be talking about the tests you could apply when you have a categorical and a numerical variable. In comparing these two types of variables, people usually divide the values in numerical variable into groups according to the categories of the categorical variable, and compare if there is any difference between the numerical values in different groups. First of all, t-test. A t-test is a type of test that used when you have two groups. Namely, there are only two categories in your categorical variable. What t-test does is to compare means of two groups and to determine how likely the difference between the two means is occurring by chance. For example, we have two variables. The categorical variable has two levels, namely two categories: taking aspirin and not taking aspirin. And your second variable is the body temperature of your patients. You put your patients into two groups according to the levels of the categorical variable. In the chart shown in the bottom right corner, two groups of patients are being compared. You want to know if aspirin can help reduce the body temperature when a patient is having a fever. The null hypothesis will be there's no relationship between the body temperature of your patients and the aspirin taking. Patients in group 1 take aspirin while patients in group 2 do not. The mean of the body temperature of patients in group 1 seems lower than the patients in group 2, but we cannot claim that they're significantly different because they look different. We conduct a t-test to compare two groups based on the mean and the standard deviation of each group and see if the difference happens by chance. That's where we need p-value, which we have mentioned at the beginning of the module, the significance level. The convention, if the p-value is less than 0.05, we can reject the null hypothesis and be confident to say that the body temperature between the two groups of patients is significantly different. The lower the p-value is, the more confident we could be. To save some space and time and to make it less confusing, we won't show the formula of t-test here. In most time, you don't have to calculate it by hand, but feel free to Google t-test formula if you're interested in the mathematical mechanism behind it. Again, t-test is used to compare means of two groups and to determine how likely the difference between the two means is occurring by chance. Beside comparing two groups, you can surely have a single value and test if the value is likely to be a part of a group using a one-sample t-test. But in this section, we only talk about the two-sample t-test, which we deal with two groups, since we're investigating bivariate analysis between a categorical variable and a numerical variable. And there are two levels in our categorical variable. Moreover, the two-sample t-test can be dependent, or we say paired, and it could also be independent. The aspirin example we saw in the previous slide is an independent t-test since we had two groups of patients. We can also test one group of patients on two different time points. For example, we can measure the body temperature of patients in group 1 before and after taking aspirin. In this case, the two levels in our categorical variable should be 2 time points. Testing on a same group with same subjects repeatedly at 2 different times or on 2 different measures is called paired t-test. For an independent t-test, since the subjects are from different groups, the distribution might be very different. We could conduct a f-test first to decide whether the variance of the two groups are equal or not, then choose the t-test assuming equal or unequal variance. Just for your information, there is a test called z-test that is very similar to t-test. However, z-test assumes that you have the data from a whole population, which is not usually possible in the real world. Looking back to our aspirin patients, our test was only able to be conducted on a very small amount of patients sampled from all possible patients in the real world. If you want to use the z-test, you will need to collect information from all patients in the world who are taking aspirin. However, if your population is relatively small, for example, students in a specific school or grade, z-test could be a good choice. When there are more than 2 levels in your categorical variable, t-test will not be applicable anymore. Here we need ANOVA. The mechanism behind ANOVA is similar to t-test. It compares means of more than 2 groups and determines how likely the difference of means among them occurs by chance. However, a significant test result from ANOVA won't tell you exactly which 2 groups are significantly different. You will still need to conduct more tests if you want a further investigation. Since t-test and ANOVA are investigating the distribution of different groups of data, box plot could be a good choice of visualization. The line in the very middle shows the median. Comparing to mean, median is less sensitive to the skewed data and can show us whether the data is skewed or not. The data is asymmetric if the line of the median is not in the middle. The box in the middle represents the interquartile, including 25% of the data lower than the median and 25% of the data higher than the median. Namely, the middle 50% of the data, ranging from 25% to 75%. And the maximum and the minimum marked in the box plot show the maximum and the minimum according to the distribution of the majority of the data, which is calculated by adding a 1.5 times of the interquartile range to the 75th percentile or minus this range from the 25th percentile. They don't necessarily represent the true maximum and the minimum of the actual data, since sometimes there could be outliers that are not within this range. The outliers are marked by dots higher than the maximum or lower than the minimum. Now let's take a look at questions for this section.